Okay. Well, first of all, thank you very much for the organizers for the invitation. It's a great pleasure to be here for Jair's party. He's an old friend, always young for me. So thank you very much for the organizers. So I will talk about vortices, but I will start with Euler's equation. That's essentially the origin of all this business. So the density of the fluid is equal to 1, and Euler's equation is this plus this equation. That's the incompressibility, represents the incompressibility of the fluid. And this equation implies this last one. This is an integrability condition for the vector field, essentially, in 2D. Everything I'm going to talk about is in 2D. So we start with R2, the simplest surface. And then this implies that V can be written as the orthogonal gradient of a function that we call a stream function. I usually put a minus sign here. So there's a minus sign, and this means that V is equal to x2 psi minus x1 psi. So this condition implies that there is always a function with this property. And we want to find a vector field that satisfies this equation and with this condition. And, well, everybody knows this is a hard problem. No, this equation has 250 years, more or less, this system. And the first thing that people did was to look for particular solutions, and the simplest solution that we can think about are the following. So I look for particular solutions first. And there is a large class of solutions that are easy to write, and they are called potential flows. And moreover, let me write something here. There's an important quantity that will appear in this talk called the vorticity. And the vorticity, what's the vorticity? The curl of V. But here, since you are in 2 dimensions, this is just, dx1 V2 minus dx2 V1. And moreover, before I talk about this particular solution, let me write the following consequence of these 2 equations. If I plug in this V here, inside here, I will get that Laplacian of minus psi is equals to omega. So the Laplacian comes to this question through this equation. So this is a key point in the talk. Anyway, but the simplest sort of solution that we can get is where we take omega equals to 0. So no vorticity at all. So this implies that we are looking for stream functions, stream functions that are harmonic. And if we also impose that, for instance, this is not necessary, but it's convenient at this point, that they are time independent, and there is this quantity here. In fact, this is the pressure, and essentially is related to this equation. You need the pressure to satisfy this equation. And in this setup, the pressure must be taken. If I get a harmonic function, so 0, for instance, can take it to 0. This constant doesn't matter. This constant, in fact, can be taken to 0. So I take any harmonic function, time independent, defines the pressure as the minus gradient of the norm of the square of this, and we get a solution of this equation. So this is the simplest class of solutions. There are plenty of them. Any harmonic function generates a solution of Euler's equation. Well, the next step was to to violate this at a single point. And in order to get something that is non-trivial, I must take omega as a delta measure, in fact. And this gamma here is a constant. is just what I will call the vortex intensity. This will be the vortex intensity. So if I take this, I must find a psi that satisfies this equation. And in other words, I'm looking for I have a variable here. Psi, let me write it more. Will be a function of x and p. P is where the vorticity, the center of vorticity. Right? And this, we know the solution to this is the fundamental solution of the Laplacian. So psi is just, maybe the sign is wrong, but anyway. It's just this. And how is the vector field associated with this psi? It's just, you have a point here, the center of vorticity, and then the trajectories of the flow rotate like this on circles. This is the point P. Well, here it's also time independent. By the symmetry of this problem, where could it go, right? Everything has this rotation symmetry, no question about. But then let's move forward. What's the next step? Next step is to take the vorticity concentrated on 2 points. So the next step is just the following. I take omega equals to the sum of the first one plus the second one, that I will denote with the tilde. And then the solutions. This is a linear equation. Very convenient, by the way. So I can just take the stream functions of the vortex independently, and then I add them. So that the solution is very easy. It's just the sum of those two other solutions. But now I have two parameters, P and P tilde is just minus gamma 2 pi. Yeah, here it's wrong, right? Because I center the vortex at P. So there's a P here. So there's another. And you write this with a different color. And that's it. So let me draw. I will keep this here. I will erase this part. Yes, because I will glue this vortex to another one. So, but now, how is the flow? The flow is like this. Now I have the first vortex at P. The second vortex I will put here at P prime. Right? This is the one, P prime, not P tilde. All right. And then, here, I don't have this symmetry anymore, the symmetry and the rotations, but so in principle, it's not natural to take this solution as a time-independent solution. So the vortex here is natural that they move. But how do they move? Well, most of you know already the answer, but I will present an argument. It's a key point here in my talk, and not in my talk, in my understanding of this question. That's the following thing. Suppose I want to keep the flow as it is, the two vortices at rest. I will hold this vortex. And I can do this through the following, mental device. I think that these two vortices are material entities. It's two cylinders rotating, and I can hold the cylinders. And then I cast the following question. What's the force I have to do to keep this vortex at rest? And it's a very simple computation, a textbook computation. Any textbook on fluid mechanics, especially those used by engineers, have the following result. So here you have a velocity. I want to put two different colors here. So I put this. This U is the velocity induced by this vortex at this point, and I put the pink here. This u tilde is the velocity induced by this vortex here. So if I take a cylinder here with an incoming velocity u, uniform incoming velocity u, as I said, this is a textbook formula that gives the force that acts here. And this force is ρ, which equals to 1, so the density equals to 1. U, the incoming velocity, times the circulation, the vortex intensity. So this is the lift. In fact, it's the lift on the cylinder. And the lift points to this direction because, you see, at this side of the vortex, the velocities add, and essentially you use an argument, Bernoulli's equation, this equation. So the pressure is lower here than here, so the force is in that direction on that vortex. And the same computations give a force that's the opposite of that one. I'm sorry, this is F tilde, right? This is F. It's just ρ equals to 1, gamma tilde times, gamma times u tilde. That's it. So I have this force. And the argument is the following. Well, so if there is a relative velocity between this point vortex and the incoming fluid, there will be a force, the lift. So the only way that there's no force on the vortex, because the vortex doesn't have any mass, doesn't have anyone holding it. There's no, the right-hand side here is just the pressure. There's no extra term here. So the only way that this can balance, can be compatible with this equation, is that this vortex have to move according to this rule. This one moves with the velocity induced by the other one of P, and P moves with the velocity induced by P tilde. So this is the case of bound vortices. In the literature, this is the bound vortices. But the free vortices move. So if you take free vortices, I will erase this. I will not need this anymore. Well, in the case of free vortices, so if I don't hold them, then the case of free vortices, so the solution will be time dependent, right? The solution will be time dependent, and what will happen is the following. This one, if this is P tilde, this one will move with the velocity u induced by this one, and the P will move with the velocity u tilde induced by this one. So these are the case of free vortices. So P and P tilde will be time dependent, so that these delta functions will move on the fluid according to this. In this particular case, they will rotate and eventually translate too, depending on if both gamma equals to gamma tilde, it's easy to say that it will rotate. Anyway, so this, the more or less, very quickly what happens on the plane. So this is the, and moreover, so you have many vortices, then you have to follow this according to this rule. So you have a set of ODEs. In other words, this is very convenient because in some sense, you have time-dependent solutions of this that can be solved using ODEs. So it's an infinite dimensional dynamical system become a finite dimensional, very particular solutions, right? Anyway, so now let me move to the case of surface. How does this work? Just, yeah, wait. So now I will move to the contribution of Jair to this field. It starts in 1985 on these papers with 3 papers, 85, 87, 89, on vortex on plane, systems of vortex, in fact. Well, you have these 2 first papers that are related to this rings of vortex, right? And then you have that one, the rigid body. You have a cylinder with vortex around it, also studying the dynamics of the system. And then you have this very nice paper from 1989, the non-integrability of 4-point vortices. Very nice paper. And then there is this 1994 paper that's, I like it very much because I'm one of the authors of this paper. In fact, it was my first mathematical paper, in fact, after my PhD. On this paper, The idea of this paper I like very much. I will just mention it because I will come back to the same idea now in a few minutes. And the idea of this paper is the following. You see, I like very much this idea of bound vortices. Moreover, this argument, bound vortices, exactly this argument here, we did, I, Jair, and Professor Valdir Oliva, using material cylinders. But there's a very elegant argument. This argument, in fact, the way I present it, is an argument in the book by Friedrich. And Jair told me about this book. Very nice book. In fact, he presented me this book. Many references, in fact, that I like very much. Jair told me about them. So this is in the book by Friedrich. But anyway, what's the main point of our paper from 1994? Is the following. I was very puzzled by this. Someone mentioned today, what are the Hamiltonians that do not come from Lagrangians, right? You mentioned, right? This is exactly one example. Yes, this is exactly one example. This is a Hamiltonian that does not come from a Lagrangian. But this is very annoying for me. You know, my training, in fact, was in physics, in fact, as a PhD. And I was very annoyed by this Hamiltonian. I did not trust it. It's a very strange Hamiltonian because the phase space is very strange. The phase space has a finite volume. If you put this vortex on a container, right, the phase space is the product of disks that has a finite volume. It's very strange because any mechanical system, what happens with the phase space? The volume is unbounded, right? The energy increases, the velocity increases, right? It's unbounded. And this is essentially, this point is at the heart of some difficulties in this field. For instance, there's this Onsager thermodynamic statistical mechanics treatment of point vortex, and he gets negative temperatures. It's related to this paradox, in fact, because the phase space has a finite volume. If you quantize a vortex system, you get a system with a finite number of eigenvalues. Energy cannot go particularly high because, the phase space is in the momentum. It doesn't go up to infinity. So it's a very strange thing. Anyway, but then, it's a really strange Hamiltonian because you can embed it in a Lagrangian, and this was my original goal in this paper. And how do we embed it? It's easier to explain the idea using an electromagnetism analogy, and I'm going to do it because I like this analogy very much. And it's the following. So you take what we did in this paper. It's a 1994 paper. It's essentially, the idea is the following. We make an analogy with electromagnetic analogy. So you take, for instance, let's study the motion of a particle on R2, charged particle. So this is the left-hand side of Newton's equation. Then you have two types of forces. I'm going to put the charge, electric charge, and then this is the Lorentz force. And moreover, I will put a magnetic field, constant magnetic field, orthogonal to the plane. So here is the plane, E1, E2, E3. So B, if you like, B is constant, equals to 1. So the B is the intensity of the magnetic field. It points towards to above. This is the Lorentz force. And then you take an electrostatic force. You have electrostatic potential. This is electrostatic. Electrostatic. The electrostatic force can be the result of the presence of other charges in the system, but let's forget about that. This is what's this? This is a four-dimensional Hamiltonian system. Very nice Lagrangian, Hamiltonian, everything. What happens if I just make m equals to 0? Suppose I make, let me take this out of here. Suppose I just take a very light particle. The mass is very small, and eventually it gets to 0. So I make it m is equal to 0. If m is equal to 0, what happens? This q cancels out, And they get this equation. And if you write this, the components, I think I get this. And this is Hamiltonian, very nice, 2D. So essentially, what happens? We just dropped out part of when you take the mass of the vortex to 0, this goes away. No. By chance, you have this, in this vorticity, this 90 degrees rotation, like a magnetic field, and then you get again a Hamiltonian system. Right? So this is the reason that I like very much the idea. Anyway, but this is our paper from 1994. But in fact, this talk, I don't know how many minutes do I have? How many? 5. Only 5. So I will start the talk now. 5 minutes. But you know. But then Jair came with this paper in 2008 with Stefanella Boato. This is a preprint, you know, lots of ideas, and lots of questions too. In the beginning, I could not understand the paper. I have to I took a look, and I had a student. I gave it to the student to read and clean the ideas in some sense. And then, but it's a very important paper. It was not published. I think this is a new version of this paper is in this 2014, right? You gave me the preprint, right? It's a very different. The 2014 paper is very different from the 2008. Very different. But many ideas are in both papers, right? And in fact, I don't know if it has been already published or not. No, not yet, right? But it will be in this Marsden Memorial volume, right? It's a nice paper, very nice paper in this volume. And there is also this, the vortex pairs on surface, a nice idea. I'm not going to talk about this paper in 2009. Anyway, but you know, but what happens here? Let me move forward. So some of history of this vortex on surface. No, you can generalize this to surface very easily. First of all, Euler's equation on surface is immediate because the generalization. Because this is just the covariant derivative. So now you have a metric. You change this by this. Gradient is the gradient, the Riemannian gradient, divergence. Everything makes sense. The Laplacian, everything makes sense. So it's more or less straightforward to do the generalization. And then the vortex, of course, the vortex must be the solution to this equation. But one thing happens. If you go to surface, the first problem that happens is the following. Take the sphere, for instance, right? The sphere, you cannot have, for instance, this equation. This equation doesn't have any solution on the sphere. No solution on the sphere. By the way, on the sphere, even this solution doesn't have any interesting solution. Because the sphere is compact with no boundary, and the only harmonic functions are the constants. So no harmonic vector field on the sphere. So it's very natural. This also doesn't have any solution. So in order to make sense of this, you must subtract something. And what is subtracted, what in fact Jair and other people did, they put a background vorticity, a constant. A constant background vorticity that, to compensate the delta function. Then this has a solution. And so this is the beginning of the story on compact surfaces. So, but anyway, but on the sphere, many people treated this problem before. Zermelo, it's amazing, right? 1902, Lamb, Gromeka, Bogomolov, etc. There's this history I got from a paper, this nice paper by Borisov, Mamaev, Ramodanov. But anyway, but in these two papers, 2008, 2014, is the first time I saw these equations written for any surface, compact surface with no boundary, right? The first time I saw it. And moreover, there's another very curious thing. Then recently, some months ago, I found this other paper. This is the physics, the physical paper. It's amazing. They have many of the same ideas in this paper. I could not really understand part of it because it's a mixture of liquid helium with superfluid, liquid crystals, everything is on that paper. But they get the right ideas. They also have been publishing on this field since the 90s. And moreover, if you take, for instance, the reference from your paper and the reference of that paper, it's almost, except for this Birkhoff, Helmholtz, I don't know, this old literature on point vortex, it's disjoint. It's amazing. But they have a lot of good ideas, a lot of nice examples, written in a different style, but essentially the same ideas, right? So these people in physics. Anyway, but so this paper, they introduced this idea, and the point is, well, what's the novelty in this business? The novelty in this setup is the following thing. Let me just take the case where you have vortex with boundaries, just to explain the idea. I will cut most of this talk, in fact, but let me explain this idea. You take a bounded domain now, and you put a vortex in the bounded domain. So what happened? A single vortex on R2 doesn't move, but a single vortex on a bounded domain move. Suppose you take this domain is a disk, for instance. This is the easiest one. What happens if you have a vortex here on a disk? The fluid cannot penetrate the boundary of the domain. So this must be a streamline, the boundary. In order to make this a streamline, you must put another vortex here, rotating the opposite direction. This rotates there, that's rotates. This is the image vortex, like an image charge. So the velocity that this vortex doesn't exist, in fact. But anyway, if you put them, you make this boundary condition okay. So this one moves according to the velocity of this one. In this case, it moves in this direction, right? So essentially, you can think it moves because the vortex is isolated, but it's interacting with the boundary, so it moves. When you have a Riemannian metric, here you have a metric G, what happens? You don't have a boundary anymore to interact with. But it turns out that the vortex interacts with the geometry. In which sense? The fluid is moving on the whole surface. And then it meets that varying geometry, and so the metric change, so the divergence change, etc., etc. And essentially, it fills all the geometry of the whole manifold through the pressure. So it moves. Moreover, I am writing notes on this because Professor Liderberto, who's here, asked me to write notes on this business, and I tried to make the analogy in this case, the Riemannian case. And the analogy is not straightforward. I don't know if the analogy happens because what happens the following: in the electromagnetic case, charges, the charge, this sort of phenomenon can happen, but it's not related to the matrix. It's related to the dielectric constant, right? The charge, if you have a varying dielectric constant, right, the medium reacts to the electric field differently at each point. And then this makes the same effect of the geometry. But the geometry itself, couldn't, if you don't put this extra ingredient, the geometry itself doesn't seem to play an important role in the electromagnetic case. But anyway, for the vorticity, so interacts with the geometry. So this is, let me go. I will jump, because my time, I think, is over, right? So I'll jump. I'm going to the open problems, right? Just the open problem. So, well, my own contribution is about non-compact surfaces. But it's a long story. Let's forget about that. Yeah. Let's go to the example. Examples, there are several too. There are examples on round sphere by many people. Ellipsoid, one of them, Regis here, Adriano Regis here, has a paper on ellipsoid. Flat tori, the Poincaré disk, the catenoid by Jair. Now I'm with my collaborator Umberto. We are studying vortex on minimal surface, on harmonic surfaces. Anyway, there are some. Anyway, but let's go to the two open problems. I like this part better than the others. First of all, there's a question on the paper by Jair. My feeling is that the answer to this question is easy, but I cannot answer it. It's the following. Well, I mentioned there are results in several circumstances, right? But there's this very simple one. To study vortices on compact surface of curvature -1, like, the bitorals, this genus 2, 3, 4, but constant curvature. So you take the Poincaré disk and take the quotient by isometries, these isometry groups, and I want to know if one vortex, for instance, move or do not move. This is a question on the paper by Jair. He has an argument to say that it moves because the group is not commutative, this group that, of isometries. This subgroup of the Möbius group, right? Anyway, but I don't know. Honestly, I don't know. I thought it would be maybe easy to answer it. I spent an afternoon trying to write the equations of motion. I could not do, but I'm sure, because this is a very classical subject. I'm presenting not easy questions, but natural questions that can be solved, not complicated questions. So this question is, I'm sure both of them can be answered in a reasonable way. The second one, maybe is this thing I like the most on this, is the following. To study a single vortex with mass on a curved surface. Now it's a general study. In which sense? The following sense. If the mass is large, so you have two quantities here, the mass and the vorticity. The vorticity here, you can think is this, well, is that gamma, right? If the mass is large, for instance, the gamma is 0, what you have in a vortex with mass, you just have the geodesic flow. You don't have anything. You have the geodesic flow. Everybody knows. So it's a huge theory now to study geodesic flows on surfaces. Lots of results. Anyway. So as the mass tends to 0, we get the integrable vortex dynamics, because the vortex dynamics is always integrable on a surface. You can show it. It's easy, right? But anyway, moreover, if you fix a compact surface, you fix, and you take large energies, you have mass now. If you take large energies, the system will approach the geodesic flow. If you take low energies, no, the velocity is very small. The inertia plays not a significant role, and you get the vortex dynamics, which is integrable. And the reason it called me attention is the following. This is completely determined by the metric. The geodesic flow only sees the neighborhood of the Hamiltonian manifold, the metric. The vortex, it looks at the whole manifold. So you have this game here. And moreover, many people studied geodesic flows under magnetic fields. And there is a magnetic field that's completely determined by the metric. It's exactly this. The magnetic field that people study in this business of geodesic flows is exactly this one. It's a constant magnetic field. It's just the area form. So here you have the area form plus this Robin function, a function that I didn't tell about. But there is this function that comes from the interaction of the surface. I think this is only geometric data. It's a very natural problem to study and can give a very nice theorems maybe. And that's it. Thank you very much.
Thanks, Clodoaldo.